Let us take some two special cases. For any point on the axis of the dipole, what is the electric potential? Look, if you select this point, say here, look, that is on the axis, okay? Then tell me, when point P is taken here, its positional vector will be like this, correct? With respect to this midpoint, positional vector will be like this, and already there in the same direction there is vector P also. So vector R and vector P will be in the same direction. If vector R and vector P are in the same direction, then angle theta between them will be 0 degree. When theta is 0 degree, cos 0 is 1. So at that time it is Kp upon R square. Here it is, Kp upon R square, correct? When theta is 0 degree. Now if you take point P on the axis, but say here, then tell me, with respect to this midpoint, position vector of that point will be like this, correct? Like this. And vector P is in just opposite direction. So vector R and vector P, when they are in opposite direction, angle between them will be theta equals to 180 degree. When theta is 180 degree or pi radian, just put it here. When theta is 180 degree, cos of 180 degree is minus 1 into Kp upon R square, that is minus Kp upon R square. Come on, minus Kp upon R square, correct? So what I mean to say, value of electric potential due to electric dipole at any axial point is either plus Kp upon R square or minus Kp upon R square. So I am writing here plus or minus Kp upon R square, plus or minus Kp upon R square, got it? Fine. Now on the equatorial line, if you select this point on the equatorial line, correct? Then tell me, if you select point P on the equatorial line, then if you take point P here, then vector R will be like this, correct? And this is vector P. So vector R is along y-axis, vector P is along x-axis. Then what is the angle between them? 90 degree. When theta is 90 degree, when theta is 90 degree, put it here, cos 90 will be 0. So at that time electric potential is 0, correct? At all the points on the equatorial line of electric dipole, come on, electric potential comes out to be 0, got it? My dears, here 2 points are very interesting. Which are those 2 points? First, if electric field is present, not necessary that electric potential also must be there. And reverse, if electric potential is there, then not necessary that electric field also must be there. When electric field is there, electric potential may be or may not be. I am showing you here. Come on this equatorial line, at all the points, come on, electric potential is 0. But there is some electric field at all these points on the equatorial line. So though potential is not there, electric field is there. Potential is not there, electric field is there. And reverse, here inside this spherical shell, electric field was 0. But at all inside points, there were some electric potential values, correct? Here inside the spherical shell, electric field is 0, but electric potential is not 0 at inside point. So what I mean to say, when potential is there, electric field may be, may not be. Here, when electric field is there, potential may be, may not be. So what I mean to say, whenever electric field is present, it is not necessary that potential must be there, correct? It may not be. And reverse, when potential is there, it is not necessary that electric field also must be there, may be, may not be. Got it? Let us go for question number 12 about equipotential surfaces. Equipotential surfaces. Look, the name itself suggests that it is such a surface on which potential at each point must be equal, correct? That is what is called equipotential surface. How would you define it? Very simple. A surface passing through points of equal electric potential is called an equipotential surface. Or if electric potential at all the points on a given surface are same, then it is called equipotential surface. Simple? Fine. Now let us see the physical importance of this equipotential surfaces. I am showing you. Surrounding to every charge, it has its own electric field, but it is not visible. Electric field you cannot see. Then just to show the presence of electric field in the diagram, we would like to have some pictorial representation of electric field, and that you can have using three methods, using either electric field vectors or using electric field lines or using this equipotential surfaces. So equipotential surfaces are shown in the diagram just to have one more pictorial presentation of electric field. So it is optional method to show the presence of electric field. Okay, fine. Let us see what is the shape of equipotential surface for a point charge. Let us see. Consider this as a point charge, say charge small q. Now you just take this charge at the center and taking some radius, say equal to capital R, you please imagine one spherical surface. Okay, you may find here circle, but in the mind you should not think of a circle, you should think of a spherical surface like surface of a volleyball. Correct? Fine. Now for all the points on that surface, what about value of electric potential? I am showing you. Come on. Electric potential at distance capital R from a point charge small q. What is the formula? K into charge upon distance. For all these points you can see which are shown with white empty circles, you can see that distances from this central charge are same. Great. And then when K is constant, Q is given charge, and when capital R values for all these points are same, naturally this right hand side will be same for all the points. That is, for all these points value of electric potential will be same. And if value of electric potential at all these points is same, then this is that surface which is passing through points of equal electric potential. That's why we call it equipotential surface. Correct? A surface passing through the points of equal electric potentials is called an equipotential surface. In case of a point charge, the shape of equipotential surface is spherical. Correct? Fine. Now, if you change the radius, you may have more than one concentric spherical equipotential surfaces in case of a point charge. If you change this radius, naturally the value of electric potential will change. But if you increase this radius, naturally potential value will decrease. Suppose at all the points on this spherical surface, suppose electric potential is 5 volt. Okay. Now if you increase the radius, when you increase this radius, electric potential will decrease. Suppose it becomes 3 volt. Then at all these points, electric potential is equal and it is say 3 volt. Suppose you are increasing the radius further, then electric potential at all these points on this surface, suppose it is 1 volt. So I mean to say, you can get more than one spherical concentric surfaces which are equipotential surfaces for a point charge located at the center. Okay. Fine. Now let us see what is the shape of equipotential surfaces for uniform electric field. For example, electric field produced by infinitely extended plane of charge having uniform surface charge distribution, you know, magnitude of electric field does not depend on the distance from that plane. Correct? What was that magnitude? E equals to sigma upon 2 epsilon 0. And because it produces uniform electric field, all the electric field lines have to be mutually parallel. And that electric field here I have shown. Look. So these parallel electric field lines and equidistant, they indicate the uniform electric field. And for such uniform electric field, this flat plane surfaces indicate equipotential surfaces. Equipotential surfaces. Okay. So in case of the electric field of a point charge, the shape of equipotential surfaces is spherical, and in case of equipotential surfaces of electric field which is uniform, the shape of equipotential surfaces is plane. Got it? Fine. Now here we have to understand one very important point. What is that important point? I am showing you. Direction of electric field here at this very point is this way, away from this positive charge this way, correct? Which is perpendicular to very small part of equipotential surface. Perpendicular, so I am just putting right angle here. Similarly, at this point also, direction of electric field is perpendicular locally to this equipotential surface. Here also, all these angles are right angles, correct? So in the figure you can see, electric field is always perpendicular to equipotential surface locally, correct? This direction is perpendicular to this surface, this direction is perpendicular to this part of the surface, this direction is perpendicular to this part of the surface, like that, okay? Direction of electric field is always perpendicular to equipotential surface locally, okay? I repeat, direction of electric field at each point on equipotential surface is perpendicular, okay? Fine. Now this is what you observe in the figure, but let us now prove it theoretically. How to prove that result? I am showing you. Consider this as equipotential surface, okay? Fine. On which I just select very closely located two points, say point P and point Q. This is point P, this is point Q. They are very closely located. The distance between those 2 points is extremely small, almost you can say they are consecutive points, like that, okay? Now, because these 2 points are very close, the potential difference between them you can write this way, VQ minus VP. VQ minus VP. Normally what is the formula? Minus integration from P to Q vector E dot vector dr. Minus integration vector E dot vector dr from P to Q, correct? But tell me, when you will require to take this integration, if path joining points P and Q is long path, correct? But here because points P and Q are very close, the path is very short. So you will not have more than one term, and if you don't have more than one term of the dot products, then you naturally will not require any summation, you will not require any integration, correct? So we just remove this integration, and remaining part I am writing minus vector E dot vector dr. Here it is, minus vector E dot vector dr. Got it? Wait. Where have you selected these 2 points? On this equipotential surface. But equipotential surface is that surface which is passing through points of equal electric potential. So if this surface is passing through these 2 points, then at these 2 points electric potential must be same. So Vp must be equal to Vq, and if Vp and Vq are equal, the difference between their values will be 0, correct? Because these two are equal, difference will be 0. Now this right hand side I have written as it is. Now find out vector E dot vector dr, 0 upon minus 1 will be 0. Now vector E dot vector dr means what? E into dr into cos theta. E into dr into cos theta, and that equals to 0. Tell me, here electric field has some value which is not 0. So E is not 0. And because you are making very small displacement from P to Q, the displacement vector, vector dr, I have just extended the direction, not the vector. Vector is very small, but the direction I have simply extended so that you can have clarity in the figure, okay? Fine. Now tell me, this vector dr is very small, and because you are making some very small displacement, dr value is also not 0. Dr is also not 0, okay? Neither E is 0 nor dr is 0, and yet this product is 0, meaning thereby cos theta must be 0. If cos theta is 0, theta must be 90 degree. That's what I written here, theta equals to 90 degree, correct? And tell me, what is theta here? It is angle between vector E and vector dr. Angle between vector E and vector dr. And if that theta is 90 degree, meaning thereby these two vectors must be mutually perpendicular. So I am writing here vector A perpendicular to vector dr. Vector A perpendicular to vector dr. But what is the direction of vector dr? This way, correct? It is parallel to surface, parallel to this part of the equipotential surface. Okay. Now tell me that part of equipotential surface, suppose it is like this, correct? So this is direction of vector dr, direction of vector dr, and where is vector E? Perpendicular to this, correct? So like this, perpendicular. Okay. So this is direction of vector E and this is direction of vector dr, or you can say it is parallel to equipotential surface. Vector dr is parallel to equipotential surface. So this is equipotential surface and this is direction of vector E. So what do you notice here? Vector is perpendicular to this part of equipotential surface. That is, locally it is perpendicular. Locally it is perpendicular, correct? At each point on the equipotential surface, direction of electric field is perpendicular to that local part of that equipotential surface. Okay. This electric field is locally perpendicular to this part of the surface. This electric field is locally perpendicular to this small part of the equipotential surface. Similarly, all these angles are also 90 degree each. Got it? Remember the conclusion. Direction of electric field is always perpendicular to equipotential surface locally. Let us go for question number 13. Here we will obtain very important relationship between electric field and electric potential. What is the relationship? I am showing you. Prove that E equals to minus dV by dr. E equals to minus dV by dr. How to prove that result? I am showing you. Suppose you consider electric field along, say, x-axis. Say along positive x-axis. Okay. If electric field is uniform and it is along positive x-axis, you can write mathematically vector E equals to Ex into I hat. Why only Ex? Because electric field is completely along x-axis, then it has only one component, which is x component, correct? And don't you know vector equals to magnitude multiplied by unit vector. Unit vector along direction of positive x-axis, it is I hat. So vector E at present, it is Ex into I hat. Okay. Now, don't you know position vector formula from 11th standard? What was that? Vector R equals to, in 3 dimensions, x into I hat plus y into j hat plus z into k hat. Now you remember the formula for extremely small displacement vector, let it be vector dr. Then instead of x you should write here dx, instead of y you should write here dy, instead of z you should write dz. That is dx into I hat plus dy into j hat plus dz into k hat. Okay, fine. Now tell me, we want electric potential difference between points P and Q, which are located very close inside that electric field. Come on, VQ minus VP, here it is, VQ minus VP. If these 2 points are very close, finally we wrote that difference like this, minus vector E dot vector dr, minus vector E dot vector dr, correct? And because these 2 points are very close, the difference between the potential values will be also very small. Let it be dV. Okay. So I am writing this difference as dV. It is very small value of electric potential difference. Fine. Now tell me minus as it is. What about vector E? Vector E is right now, come on, Ex I hat. Here it is, Ex I hat. Dot. What is vector dr? Right now it is dx I hat plus dy j hat plus dz k hat. Same formula written here, dx I hat plus dy j hat plus dz k hat. Just take the dot product, come on, minus as it is, Ex into dx, I have written here, Ex into dx, but I hat dot I hat is 1, and then after I hat dot j hat is 0, I hat dot k hat is also 0, correct? Fine. So dv equals to minus Ex dx, minus Ex dx, correct? Now find out Ex from here, it will be minus dv by dx, Ex equals to minus dv by dx. Tell me, when you can represent electric field this way, provided it is completely along x-axis, correct? But if electric field is along y axis, then similarly you may get the result Ey equals to, come on, minus dV by dy. Similarly, if electric field is along z axis, then you can just write this formula Ez equals to minus dV by dz. I repeat, this is the formula to be applied for that electric field which is along x axis. This is for that electric field which is along y axis, and this is for that electric field which is along z axis. Got it? Fine. Now consider this as three-dimensional Cartesian coordinate system. So this is x axis, this one is y axis, and this one is z axis. You have so far considered electric field either along x axis or along y axis or along z axis, but not necessary. Electric field can be in a direction other than these three directions. Okay, in three dimension, suppose it is along vector r, which is neither x axis nor y axis nor z axis. Okay, if electric field in general in three dimension has the direction of vector r, which is not x or y or z axis, then it will have in three dimensions all the three components. It will have x component also, y component also, and z component also. Then in that case, how will you find out those components, and ultimately how will you find out resultant electric field? I am showing you. Look, vector E in three dimension, at that time you can write this way: Ex I hat plus Ey j hat plus Ez k hat. That is for sure. In 11th standard you had studied three-dimensional representation of a vector, vector capital A. Remembered? Ax I hat plus Ay j hat plus Az k hat. Similarly here, vector E equals to Ex I hat plus Ey j hat plus Az k hat. Correct? But now the question is how to find out these components. I am showing you. At that time, x component of electric field you can write this way: minus del V by del x. Minus del V by del x. Then you may surprise, what is this del by del x? It is called partial derivative. Partial derivative. Why not complete derivative? Why partial derivative? I am showing you. Wait. Come on. How will you find out this y component of electric field? Similarly, like this, minus del V by del y. And similarly, z component of electric field you can find out this way: minus del V by del z. What are del by del x, del by del y, del by del z? They are called partial derivatives respectively with respect to x, y and z. How partial derivatives differ than complete derivative? I am showing you. Wait. When you are talking about dv by dx, here d by dx means complete derivative. And when we are talking about del by del x, you are talking about partial derivative. Okay, the pronunciation is del, that is del, and the method of writing that notation is this: minus del V by del x. Okay, wait. Now, why is partial derivative? Why not complete? I am showing you. See, at a given point, say point P, in three dimensions you will have three coordinates of that point: x, y, z. You are finding electric field at that very point. If electric field in three dimensions has all the three components, then the potential value at that very point will depend on all the three coordinates of that point. So capital V, which is electric potential, will be a function of x coordinate also, will be a function of y coordinate also, will be a function of z coordinate also. Though electric potential value is a function of three coordinates, then also you are taking here derivative with respect to only one coordinate. That's why it is not complete derivative, it is partial derivative. We call it partial derivative, and the symbol is this: del by del x. Similarly, this is partial derivative with respect to y. This is partial derivative with respect to z. Correct? But how does partial derivative differ than complete derivative? Whenever you take partial derivative with respect to x, you are supposed to take y and z as constants. Whenever you take partial derivative with respect to y, you are supposed to take x and z as constants. And finally, when you take partial derivative with respect to z, you are supposed to take x and y as constants. Okay, please remember. Fine. Now, once you find out all these three components, then you can just put them here, and then you will get complete, that is total resultant electric field at a given point. Okay, fine. Now, if electric field is only along x-axis, you may write minus dV by dx, only along y-axis minus dV by dy, only along z-axis then minus dV by dz. But in general, if it is along vector r, then that electric field you may write this way, E equals to minus dV by dr, minus dV by dr. What do you mean by dV by dr? Change in potential with respect to distance. Change in electric potential with respect to distance, it is called potential gradient. Come on, potential gradient. Can you remember two words which you studied in 11th standard? One was velocity gradient. What was that? dV by dx. Rate of change of velocity with respect to distance, it is called velocity gradient. Second word was temperature gradient, dt by dx. Rate of change of temperature with respect to distance. Similarly here, rate of change of electric potential with respect to distance, we call it potential gradient. And here electric field comes out to be negative value of potential gradient, negative value of potential gradient. Here I have written negative value of potential gradient. Electric field at any point is nothing but negative value of potential gradient. Got it? And what is the unit of electric field from this formula? Unit of potential is volt, unit of distance is meter, volt upon meter. Remember I told you two units of electric field in first chapter. First one was Newton upon Coulomb and second one was volt upon meter. At that time I told you that whenever that point comes in second chapter, I will tell you about this unit also. That point is this only. Come on, unit of potential is volt, unit of distance is meter. That's why second SI unit of electric field is volt upon meter, volt upon meter. Okay, fine. My dear, one very important note, look. dV is this much, correct? dV is this much. Now you just do one thing. In the electric field, you just move in the direction of electric field. If you move in the direction of electric field, what will happen? The displacement is in the direction of electric field, then these two vectors will have same direction, because direction of displacement is in the direction of electric field. Okay? When these two vectors have same direction, angle between them will be 0 degree. Cos 0 degree is 1. So plus 1 into minus 1 will be minus. So dV value will be negative. When change in potential is negative, it indicates decrease in electric potential, decrease in electric potential. So remember, whenever we move in the direction of electric field, potential decreases, okay. Now think of reverse case. If you move in the direction opposite to electric field, if you move in a direction opposite to electric field, then direction of displacement and direction of electric field are opposite, then angle theta between them will be 180 degree. Cos of 180 degree is minus 1. Minus 1 into minus 1 will become plus 1. That is dV will be positive. dV will be positive. When change in potential is positive, it indicates increase in electric potential. Increase in electric potential. Okay? So just remember, whenever we move in a direction opposite to electric field, electric potential will increase. Here it is. If you move away from this positive charge, tell me, don't you know formula for electric potential due to a point charge? KQ upon R, correct? When you increase this distance, naturally potential will decrease. But when you are moving away this way, where are you moving? You are moving in the direction of electric field, correct? So when we move in the direction of electric field, potential will decrease. Just speak opposite. Whenever we move in a direction opposite to electric field, then the potential will increase. Last time, when we move in the direction of electric field, potential decreases. When we move in a direction opposite to electric field, then potential increases. Right? Come on, my dears, let us proceed further in chapter number 2. Let us begin now question number 14. It is about electric potential energy of an electric dipole in external electric field. First of all, try to understand how does an electric dipole have some electrostatic potential energy inside the external electric field. How does it have that energy? I am showing you. Consider one uniform electric field which is shown in the diagram with the help of these electric field lines, you can see all of them are mutually parallel. Not only that, perpendicular separation between each two consecutive field lines is same everywhere. Okay? This indicates uniform electric field. Let it be vector E. At present it is towards right hand side. Fine. Now that electric field I am showing here, look. Now in this electric field we just consider some electric dipole having its dipole moment, suppose in the direction of external electric field. So in this figure you can see vector P and vector E, they both have same direction. Okay, fine. Now tell me, if both of them have same direction, then angle theta between them will be 0 degree, isn't it? Then recall the formula for torque. What was the formula for torque exerted on electric dipole when placed in external uniform electric field? What was that formula? P E sin theta, tau equals to P E sin theta. But at present theta is 0 degree. So sin 0 degree is 0. Ultimately torque will be 0. If torque is 0, then this dipole will remain stable in this condition itself. Okay, fine. So unless and until you exert some external torque, this dipole is not going to rotate, it will remain in the same condition. Okay, that's why we call it stable equilibrium condition, stable equilibrium condition. But now I want that this dipole should make some angle with this external electric field, and for that purpose what should I do? I must exert some external torque so that it can make some angle with this external electric field. But while exerting that torque, I have to do some work, and depending upon the amount of work, I need to spend some energy also. So at that time, energy spent by me gets stored in that electric dipole in the form of electric potential energy. That's why it possesses that energy, and that's why we require to derive its expression. Okay, fine. Now consider this figure, in which you can see there is one electric dipole whose negative charge is here. I written here minus q, whose positive charge is here plus q. Where is the direction of electric dipole moment vector? Vector small p, from negative to positive charge, from negative to positive charge, in this direction. It is vector small p, and you can see it makes angle theta with this external electric field. Correct? Now, in order to rotate this dipole from this condition to this condition, I need to spend some energy, and that energy will be stored in this electric dipole in the form of electric potential energy, which I require to find out. Okay, fine. At present, you can see distance between these two unlike charges is 2a. Correct? Tell me, if you draw one perpendicular like this is right angle. In this right angled triangle, find out cos theta. What is cos theta? Cos theta will be adjacent divided by hypotenuse. So cos theta will be this adjacent side divided by hypotenuse, which is 2a. Okay? Or if you want to find out this adjacent side or adjacent component, how can you find out? Component of 2a adjacent to theta. Component of 2a adjacent to theta. What is it? 2a cos theta. Component of 2a adjacent to theta is how much? 2a cos theta. And that's what I have written here. This much length is 2a cos theta. Correct? Fine. Come on, my dears. Here we have applied electric field along, say, positive x-axis. Correct? If electric field is applied along positive x-axis, it will have only x component, that is Ex. Correct? No y component, no z component. Fine. And in the last period, we had derived one formula for Ex. What was that? For electric field applied along x-axis, what was Ex? It was minus dV by dx. Remembered? For electric field along y-axis, what was it? Ey equals to minus dV by dy. Along z axis, Ez equals to minus dV by dz. So, right now it is Ex, so I should write minus dV by dx, correct. But if the values of changes are rather big values, then instead of writing these differential symbols, you may write symbols like this delta. They indicate rather big values of changes, okay, fine. Minus sign as it is, instead of dV, you may write delta V, instead of dx, you may write delta x. But tell me, what is this delta V? Delta V is the change in potential, that is potential difference between 2 points which are separated on x axis by distance delta x. I repeat, delta V is the electric potential difference between 2 points having difference in x coordinate equal to delta x. Alright, fine. Now this minus sign as it is, delta V as it is. But what is delta x? Change in x coordinates. Wait. Suppose you consider here origin, correct? Here if you consider origin, at origin what is x coordinate? 0. For this point, if you draw perpendicular like this, then for this point its x coordinate will be this much, correct? Fine. So here x coordinate is 0 and here x coordinate is this much. So change in x coordinate will be this x coordinate minus 0, that is this much, okay, and that change in x coordinate delta x would be this much, which is component of 2a adjacent to theta. Come on, in this right angle triangle, component of 2a adjacent to theta, this much. How much it is? 2a cos theta. Component of 2a adjacent to theta is 2a cos theta. That's why this delta x is right now 2a cos theta, correct? Fine. And now the change in electric potential energy for this electric dipole when you rotate from this condition to this condition, correct? That change in electric potential energy I am taking by symbol delta U. What was the formula for electric potential energy? Capital U, last time we had studied. U equals to Q into V, correct? Now it is not U, it is delta U. So you should write Q into delta V, Q into delta V. Here change in potential energy, so here change in electric potential, simple. Now this Q as it is, but find out delta V from here. Delta V will be how much? Transfer this minus sign here and transfer this, okay? Then delta V will be minus 2a into E into cos theta, minus 2a into E into cos theta, correct? Now this minus sign as it is, 2a into Q I am writing in bracket, into E into cos theta. But what about delta U? Change in potential energy. Remember, absolute value of potential energy is not important in physics. What is important? Change in potential energy, correct? So whenever you take change, it should be always final minus initial, final minus initial. But absolute value of potential energy is not important, so initial potential energy you can assume any value. If you can assume any value, then for the sake of simplicity we take initial potential energy to be 0, correct? So initially I am taking potential energy value 0, finally I am taking capital U, then what is the change in potential energy? Final minus initial, that is U minus 0, correct? Fine. Now this U minus 0, that is U, this minus sign as it is. What do you mean by 2a into Q? Come on, product of magnitude of either charge in a given electric dipole and distance between two unlike charges in that dipole is nothing but electric dipole moment, small p, correct? And this E as it is, cos theta as it is, correct? So what is the formula of electric potential energy of electric dipole when placed in external electric field? What is the formula we got? U equals to minus P E cos theta, minus sign as it is, But what do you mean by Pe cos theta? It is nothing but vector P dot vector E, correct? Fine. Now, let us consider some of the special cases one by one. Special cases. First, we talk about stable equilibrium condition. Stable equilibrium condition. In this stable equilibrium condition, vector P is very much in the direction of vector E. Because these two vectors have same directions, naturally angle between them will be 0 degree, correct? Put theta equal to 0 degree here, and cos 0 degree is 1, so it is minus Pe, minus Pe. Here we are going to have 3 values of electric potential energy. Among those 3 values, this is found to be minimum. That's why I am writing here U minimum, U minimum, okay, fine. Now, in this condition, this electric dipole has minimum potential energy. When potential energy is minimum, stability will be maximum, correct? And that's why we call this condition as stable equilibrium condition. Why equilibrium condition? Because there is no torque exerted on this dipole in this condition. Tau equals to Pe sin theta. Theta is 0, torque is 0. This dipole will remain like this only steadily, okay? So it is called equilibrium condition. But why do we call it stable equilibrium condition? Because though you may rotate through any angle, ultimately the dipole will come in this same condition once again. That's why it loves to remain in that condition. It likes to remain in that condition. We call it stable equilibrium condition. Stable equilibrium condition. Okay, fine. Then we go for second condition, unstable equilibrium condition. Look, consider an electric dipole having dipole moment just opposite to external electric field. Because these two vectors right now in opposite directions, angle theta between them will be 180 degree. Put it here. When theta is 180 degree, cos 180 degree is minus 1, minus minus plus P into E, plus P into E. Among the 3 values here, this is found to be maximum. That's why I am writing U maximum, correct? Fine. Now, why do we call it equilibrium condition? Because in this condition also, torque is 0. You know torque formula, tau equals to Pe sin theta. When theta is 180 degree, sin theta is 0, torque is 0. Because there is no torque, this dipole will remain like this only. But then, why do we call it unstable equilibrium condition? The reason is that if you disturb it even slightly, then also it doesn't come back in the same condition, it comes back in this condition finally, okay. So, this is unstable equilibrium condition, correct. Last time in chapter number 1, I had given 2 examples, remember? There was a marble which we had taken, and when we put it in a bowl, correct, which is kept on the horizontal surface, that marble in the bowl comes at the lowest height, at the bottommost position, correct. That was stable equilibrium condition. And then if you keep the bowl inverted, and then at the top slowly and carefully if you put that marble, then it may remain in that condition steadily unless and until you disturb it. Once you disturb it, it doesn't come back in the same condition, okay. So it was unstable equilibrium condition. Remember, marble inside the bowl and marble on the top of the bowl. Remember that example? Fine. Here in the third case we take maximum non-equilibrium condition. Look in the figure. Suppose dipole is placed in external electric field such that its dipole moment makes angle 90 degree, okay. If it is so, then we call it non-equilibrium condition. Why? Because torque is maximum. What is torque formula? P is sin theta. Theta is 90 degrees, sin 90 will be 1, this is maximum. When maximum torque is exerted on this dipole, it won't remain in this condition even for a fraction of second, correct. That's why it indicates maximum non-equilibrium condition. What about potential energy? When theta is 90 degree, just put it here, cos 90 is 0, U equals to 0. Though this value is 0, don't misunderstand, it is not minimum, because less than 0 we have got this negative value, है ना? This negative value is smaller than 0. So we have got in all 3 values. Come on, minus PE, 0, plus PE. Look here, minus PE, 0, plus PE. Among these 3 values, minus PE is minimum. That's why I am writing U minimum. Plus PE is maximum. That's why I am writing U maximum. Got it? Fine. Now, my dears, we go for question number 15. This question is very important from understanding point of view, purely theoretical discussion, no derivation, no mathematical formula. I just appeal everybody to take very special interest in the discussion, please. What is the question is about what? I am showing you. This question is about behavior of good conductor, that is metal, in external electric field. My dears, here in the textbook and in many other books,